Almost every star in the universe ends the same way. Not with an explosion, but quietly, by turning into a solid. One of them sits 48 light-years away, and it is already beginning to turn to crystal. Astronomers found it in the southern constellation Centaurus. They nicknamed it Lucy, after the Beatles song about diamonds in the sky, and the name stuck. The press ran with it. Headlines called it the largest diamond in the galaxy, a jewel the size of a world. The logic looks airtight. Its core is carbon. Carbon under pressure becomes diamond, therefore, a diamond the size of a planet. It is a genuinely beautiful image, but it is wrong. Wrong in very nearly every way that actually matters. Start with sheer scale. Lucy is not the size of a galaxy, or even the size of a star. In fact, it is smaller than the Earth. Its radius is only about 4,000 kilometers, roughly 2/3 the width of our own planet, and no more than that. And yet, it carries more mass than the Sun. Around 1.1 solar masses, crushed and packed inside that tiny ball. Which works out to something like 1 whole ton of matter squeezed into every single cubic centimeter. A teaspoon of it would outweigh a car. A matchbox full of it would outweigh an entire house. And at that density, ordinary chemistry simply stops working. The atoms are crushed flat, and the bonds that make a diamond cannot survive. So whatever is crystallizing deep inside Lucy, it is not a diamond. It quite literally, physically, cannot be one. But something in there genuinely is crystallizing. That part is completely real, and it was only confirmed for certain a few years ago. Which leaves us with a much harder question. How do you ever find out what is happening deep inside a dead star? You cannot land on it. You cannot cut it open. It is smaller than a planet, denser than anything on Earth, and 48 light-years away from us. For 50 long years, nobody could prove a single thing. The idea itself was old. Back in the 1960s, physicists worked out on paper exactly what should happen inside a slowly cooling white dwarf. A white dwarf is what most stars leave behind. It is the naked, exposed core, left over after the outer layers drift away. It makes no new energy of its own. There is no fusion left inside it. Everything it still shines is simply heat left over from before. And so it can only do one thing: cool. Slowly, steadily, for billions of years, radiating into the dark. And as it cools, the carbon and oxygen packed inside must eventually slow down and stop moving past one another. The interior would stop behaving like a fluid and lock into a rigid lattice. The star would freeze, slowly, from the center outward. It was a clean, elegant prediction, straight out of the equations. But a prediction about the inside of something nobody can ever open is not worth very much on its own. To test it, you would somehow have to catch stars in the very act of freezing. But the trouble is, freezing does not look like anything. From the outside, a white dwarf is just a faint dot of light. Frozen solid or still fluid, it looks exactly the same. You would need the brightness and the distance for an enormous number of them, all measured precisely. And that, right there, was the wall. White dwarfs are dim, and distance is the single hardest measurement in all of astronomy. Get it wrong, and every other number collapses with it. So the prediction simply sat there, untested. 50 long years, quietly waiting for an instrument that did not yet exist. The breakthrough, when it finally came, did not come from looking harder. It came from something that everybody already knew. Freezing is not a passive, quiet thing. When a liquid turns into a solid, it does not just lose energy, it actively gives energy back. You have seen it happen. A pond ices over more slowly than you would expect, because the freezing itself fights back against the cold. Physicists call it latent heat. To turn any liquid into a solid, you have to take energy out of it. And all of that energy has to go somewhere. Inside a white dwarf, exactly the same thing happens, but on a scale that is genuinely difficult to take seriously. As the core crystallizes, it dumps all of that latent heat back into the star, and therefore, the cooling does not simply continue. It stalls. The star holds at almost exactly the same brightness, while the freezing slowly works its way outward. For roughly 1 billion years, a crystallizing white dwarf is quietly propped up, held in place by its own freezing. And that, right there, is the reframe. You do not need to see inside the star at all. You only need to notice that some of the stars are stuck. Because if freezing pauses a star, then frozen stars should pile up, gathering together at one very particular brightness. Not one star, thousands upon thousands of them, all caught at the same stage, sitting in the same place on a graph. The evidence would not be a photograph at all, it would be a traffic jam, and all you had to do to find it was count. Which is exactly what Gaia was built to do. A European spacecraft, patiently measuring the positions and distances of well over 1 billion stars. And among them were hundreds of thousands of white dwarfs, essentially every single one within 100 parsecs of our own sun. Plot their brightness against their color, and the cooling sequence should run perfectly smooth, hot to cold, with no interruptions. But it did not run smooth. There was a pileup, a dense, unmistakable clump of stars, all bunched at one single stage of cooling. Far too many of them, all sitting at the very same brightness, exactly where the theory had predicted freezing would hold them in place. Published in the journal Nature in 2019, it was the first direct evidence that white dwarfs really do crystallize. A 50-year-old prediction, confirmed by a bulge in a graph. And Lucy gave a second, independent line of evidence. It pulsates, and the exact way a star rings depends on what it is made of. So astronomers listened carefully to that ringing, and around 90% of Lucy, they found, has already turned solid. So we now know for certain that it is freezing, which brings us right back to the real question. What is actually down there? Not a diamond. The electrons have been stripped away from their atoms entirely, into a single sea that flows through the whole star. What actually crystallizes is the bare nuclei themselves. Carbon and oxygen, slowly locking together into a rigid, body-centered cubic lattice. Physicists call this strange structure a Coulomb crystal. It is held together not by chemical bonds, but purely by raw electric charge. A crystal of carbon the size of a planet, carrying the mass of a whole star. Astonishing, and simply not a gemstone. The Beatles' nickname is a poem, not a measurement. What is actually down there has no real counterpart anywhere on Earth. But the strangest part of all is not what Lucy is. It is how astonishingly little of the whole process has actually happened yet. Cooling a white dwarf all the way down to true darkness takes something close to 10 to the 15th power years. 1,000,000 billion years. The universe itself is only 13.8 billion years old. It has not yet had anywhere near enough time to finish even one. Which means there are no black dwarfs, not a single one, anywhere in the cosmos. Every crystallizing star we can see is still at the very beginning. And in about 5 billion years, our own sun will join them. It will shed its outer layers, and the core it leaves behind will slowly begin to freeze. Long after the very last star has burned out, the universe will be a vast, dark field of crystal. Still cooling. Still, even after all that unimaginable time, not quite finished.